Welcome back, beautiful people. We are finally at part 3 of the CSET series.
Let's get straight into it. We are asked to evaluate the integral of 18x to the 5th times x third minus 5 all to the 4th dx. The first step will be to evaluate our options or integration techniques. The first option we can look into is one that I like to call the basics, which is the formula for integrating x to the n, which results in x to the n plus 1 all over n plus 1 plus c. Don't forget that constant. If we were to compare this to taking the derivative of x to the n, we can see that we are almost performing the exact opposite operations from a derivative, hence why integrals are thought of opposites of derivatives. However, for our example, this basic technique doesn't work well. So what should we do then? The second option I like to look into is ways to rewrite our given integral. We can perform some algebra to rewrite it, maybe some other technique. Well, algebra isn't the best option for this instance because it could definitely make life harder. That x cubed minus 5 to the 4th, if we were to expand that, we would end up creating a lot of work for ourselves, so no thanks. So what other technique could we use then? Well, the second technique I like to look into is u-sub or u-substitution. The key here is finding a u that has a derivative that will align with the other half or the other section of the integral. Well, let's get into it in practice to better understand what that even means. When taking the u substitution, we will have multiple options to choose for u. A first option would be choosing 18x to the 5th as our u. In that case, our du, which is just a derivative of u, would be 90x to the 4th dx. And don't forget that dx either. So you know what? I'm actually going to make finding u and du step 2a. Because once we have established that, then we can rewrite the whole entire integral. So let's take a look at 90x to the 4th. The key here is to see if this is a good fit for the other half of the integral that we haven't chosen for our u, which in this instance is x to the 3rd minus 5 all to the 4th. While both have the exponent of 4 in common, that 90 doesn't really match up well, especially with the polynomial of x cubed to the 5th. So if we were to try to substitute the du for that section, it just wouldn't fit or align nicely. But let's say you're overly ambitious and you want to try it out anyways. We can start off by subbing in our u, since it matches perfectly with the 18x to the 5th because we chose it. Then we would need to solve for dx because we want our new integral in terms of u. So let's solve for dx. At this point, we can now substitute. There's a lot of subbing going in. We can substitute our du over 90x to the 4th back into our integral. However, we still have x's, and we want only terms of u. So then we're going to want to solve for x. We can do so by using our u formula. If we were to try this out, we would end up having a 5th root of u over 18. No thank you. That does not look fun to deal with. So let's try another option. Let's try the whole x to the 3rd minus 5 all to the 4th as our u, or the other section of the integral. Our du would end up being 12x squared times x to the 3rd minus 5 to the 3rd dx. Now that's a pretty complicated du in my opinion. So to be honest, I don't even want to try this out. We're just going to move on to our final third option. we can actually just use that x third minus 5 as our u. And we would get du equals 3x squared dx. So let's just try this one out. We sub in our u. We need to solve for our dx. We find that dx equals du all over 3x squared. If we were to try to sub that in before we come to a conclusion that we can't do this either, there's actually some handy dandy algebra that we can use. 18x to the 5th over 3x squared can be simplified. They can be simplified because their base of x is the same. So we end up getting the integral of 6x cubed times u to the 4th du. But once again, we need this in terms of u only. So what can we do? Well, if you look at our u formula, we have an x cubed in common. So let's try to solve for simply x cubed. We end up getting u plus 5 equals x cubed. We can actually use this to sub in to our integral. We end up with 6u to the 5th plus 30u to the 4th du. Now this is something that looks a little bit more friendly. So going with this route, we're going to move on to step 3, which is to evaluate or solve our u integral. And here we don't have anything too complicated. We can just use the basics. While it might be tempting to say we're done here, we are not done just yet because we need to continue simplifying at this point, and we want to change our u function into an x function. So let's simplify as much as we can. If you stop here, it isn't wrong, but sometimes it makes life easier when you continue to simplify as much as you can. Then we'll want to use u equals x to the 3rd minus 5 to substitute and rewrite our function in terms of x. And now we finally have our answer. X cubed plus 1 times x cubed minus 5 all to the 5th plus our constant. Nice! So all this substituting back and forth may seem overwhelming, but the more you practice and set your own steps in solving u-sub, because the ones I'm providing are simply guidelines, the easier solving will become. So now try question 1b, which does involve boundaries. I have written my guidelines, the steps that I would take, and you would want to start off by evaluating which integration techniques is best. And hint, hint, we are using u-substitution as practice, but still try to process step 1 on your own. I do suggest breaking this thought process down until it becomes more natural for you. You will want to then rewrite the integral by choosing your best option for your u. And once you do that, you'll want to solve and rewrite into an x function to finish off the problem. I already want to point something out here. Actually, some of you might rewrite this integral using algebra, which is great. It's a great technique to use. I do actually recommend it. You can simply expand this polynomial and then use our, once again, what I like to call our basic technique. And you can definitely solve this problem that way. But to continue practicing, I'm going to solve this using u-sub, and I encourage you to try it along with me just for the sake of practice. So let's review together how we could go about solving a definite integral using u-sub. When we're trying to evaluate the u-integral, we're going to want to keep our boundaries in mind. So I like to use u1 and u2 to represent my potential u boundaries, which are not necessarily equal to my x boundaries. This is dependent on our u function, the one that we chose. So in that case, we have two routes we can take. The first, which I'll call step 3a, solving the u-integral directly, will actually use u boundaries. The alternative route, which I'll call step 3b, will involve rewriting to an x function and then evaluating with x boundaries. So let's start off trying 3a. The first step is to find our actual u boundaries. Our u function is u equals x plus 1. So using our given boundaries, we can substitute the 2 and 5 to find our u1 and u2, which turn out to be 3 and 6. Then we will evaluate the integral using these boundaries. And we end up with 63. So let's check if our alternative route gives us the same answer. For the alternative route, once we solve the u integral, we'll want to rewrite into an x function. So we'll want to sub that x plus 1 back in. And now we can evaluate using our x boundaries or the original 2 and 5 boundaries that were given to us. After evaluation, we end up with, what do you know? 63. So for question 2a, it states, find the area of the region bounded above by the graph of y equals inverse of tangent x and below by the x-axis over the interval from 0 to 1. So the first step I would take is to evaluate our word problem. I ask questions like, what am I confused about? What do I need to better understand? What is the given information and what exactly is being asked? Maybe the bounded above by and below by is confusing, so we can take a look at that. When it comes to the given, the boundaries are given as an inverse of tangent, x-axis, and we're given a closed interval. And finally, we are being asked to find the area bounded by these boundaries. So if for some reason we misread what's highlighted in green, maybe it's that by that might be confusing us. So what I would recommend is graphing. When in doubt, graph. So if we misread this, and let's say we just completely overlooked the by, and we read it as bounded above the graph of inverse of tangent and below the x-axis, in this case, the area we have just drawn don't even overlap to create one region, be some alert that we have done something wrong. So if this is confusing, here are some alternative ways to write and understand what this boundary statement is even saying. It's stating that the graph inverse of tangent x is our upper boundary and that the x-axis is the lower boundary of our region. Or in other terms, this region is bounded by the curves y equals inverse of tangent of x and the x-axis. So let's try graphing that correctly this time. And we should end up getting something like this. And we actually have one more piece from our given information, which is our closed interval, meaning that our x values are between 0 and 1, and therefore our region is constrained between these values. And this is our region that we're analyzing. So at this point, what is it that we're trying to find again? It asks us to find the area of the region, or in other terms, you may have heard it as the area under the curve. These words should spark integrals. So step 2 will be to set up our integral and evaluate the techniques we can use to solve this problem. So when we're setting up the integral for a region like this, we want to take the integral of the top boundary minus the bottom boundary. And be careful not to forget that our x-axis is a boundary. Then we will want to proceed with finding the best way to solve this. So u-sub wouldn't actually be a very friendly technique to use in this situation. So what other techniques do we know? Well, how about integration by parts? Let's try that one. Using this technique, we will rewrite our integral into uv minus the integral of v du. I like to set up my terms in this format personally because then I like to draw this arrow to indicate the order that I will be rewriting the integral. Okay, so the two terms that will come from our integral is u and dv. So for example, u can be the inverse of tangent of x, and therefore that derivative would be 1 over x squared plus 1 times dx. So whatever's left from our integral will be our dv. In this case, it's simply dx. Our v is the antiderivative or the integral of dv. So in this case, the antiderivative of dx is just x. Now we can set up our equation, which is u times v, or in our case, the inverse of tangent times x, evaluated between 0 and 1, all minus the integral of those same boundaries, 0 and 1, of v times du, or in our case, x all over x squared plus 1 times dx. And both of these sections look good to solve, so let's go with this integration technique. I'm going to solve these sections separately. On the right side, after assessing the integral, I'm going to choose u-sub to solve this side. But before then, let's solve the left side. To find what the inverse tangent of 0 is, let's use this unit circle. You can check out part 1 of the CSET series where we do go over trig in more detail. I'll link the description down below. So the question here for the inverse of tangent of 0 is, when will tangent be 0? If we take a look at our point at 0, our coordinates are 1, 0, and tangent equals y over x. Or at this point, 0 over 1, which is just 0. Therefore, when our angle is at 0, which is our answer, tangent equals 0. So now let's try inverse tangent of 1. Where is tangent equal to 1 on the unit circle? Well, at this point, we have the coordinates the square root of 2 over 2, comma the square root of 2 over 2. If we take the tangent, which is again y over x, we get 1. Therefore, the angle at this point, which is our answer, is pi over 4. So that means that the left side is simply pi over 4. Now for the right side, we'll want to use u-sub. To properly set up for our du, we can multiply our integral by 2. But then we'll have to compensate by multiplying everything by 1/2. We want to use this strategy to help us rewrite our u integral as simply du over u. And when we compensate, we'll want to carry that 1/2 over. Remember, there are two ways to solve du for a definite integral. Either we directly solve the u integral with u boundaries, or we end up rewriting to an x function and evaluate with x boundaries. So for extra practice, we'll solve for both, starting with the left side or our u integral. We'll want to find our u boundaries to continue solving. A reminder that the integral of 1 over u is a natural log of u. So we'll end up with 1/2 times the natural log of 2. So now let's try the right side. This is the point of the process where we will rewrite in x terms, and we will evaluate with our given x boundaries. And when you look at that, both strategies in solving u-sub look exactly the same. A quick note and friendly reminder that the natural log of a minus the natural log of b equals the natural log of a over b. Hence why we end up with 1/2 of natural log 2. While we want to celebrate all this hard work, don't forget that we are not done because we can't forget our pi over 4. So putting everything together, we end up with pi over 4 minus the 1/2 natural log 2, and that is our final answer. So how about you try 2b? You got this. Don't forget to double check your algebra. This is one area where we make the most mistakes. So dividing by a fraction is the same thing as multiplying by its reciprocal. So quickly, I want to review the cosine of pi over 2 together. The question to ask ourselves here, which is different than the question we asked ourselves when looking at the inverse of tangent in our previous problem. The question to ask here is, what is the x-coordinate, since the x-coordinate is connected to cosine, at pi over 2? The x-coordinate at this angle is 0. So cosine at pi over 2 is 0. Now cosine of 2 times 0 is cosine of 0. What is the x-coordinate at angle 0? Which actually is 1. But 0 times 1 over 2 is simply 0. Meaning that this left side just ends up being 0. So that's pretty easy. Moving on to our integral section, to our right side. So now continue solving for the right side. At this point, you get to choose which method you want to solve for your definite u integral. If you haven't checked it out, once again, check out the trig video of the CSET series, where I explain that the sine is connected to the y. So we're looking at the y coordinate at pi over 2 and 0, which is 1 at pi over 2 and 0 at 0. Hopefully you also end up with 1/4, or option D. And lastly, we have question 3, which states, the acceleration of a particle as it moves along the x-axis is given by d squared x over dt squared equals to 12t minus 2 meters per second squared, where t is in seconds. For step 1, let's evaluate this word problem, just like we did in question 2a. We'll want to look at what's confusing us, what's given, and what's being asked of us. So this notation might look a little scary, so I'm going to want to make sure that I understand what it means. It's also connected to a given formula. In that case, I really want to make sure I understand what this means. We're also given that at t equals 1, the particle's position is at x equals 3 meters, and its velocity is 0 meters per second. We're being asked to find the position at t equals 3 seconds. So first, let's make sense of this derivative notation. This is actually telling us our acceleration. This particular notation is the notation for a second derivative. And in this case, it's the second derivative of our position function. So a quick review, if we need to go from acceleration to position, we'll need to find first the velocity, which is the integral of our acceleration, and then the position function, which is the integral of our velocity. Now let's say we started with our position and had to find acceleration. Then we'll be taking the derivative twice. In other words, the second derivative of our position function. But when moving from acceleration to position, we don't take the second integral. This notation I've written here is actually a whole other realm of calc that we won't want to get into for this exam. So for our problem, we'll be taking the derivative of our acceleration and then the derivative of that velocity that we find. So let's start by finding velocity. We'll take the integral of 12t minus 2 dt. We are left with a constant, which we will now use our given information to solve for. We are told that at t equals 1, the velocity is equal to 0 meters per second. So if we substitute 1 for our t and set the equation equal to 0, we can then solve for c. And we end up with c equals to -4. Now we can finish writing our velocity equation. The next step, we'll take the integral of this formula that we just wrote to find our position function. And once again, we end up with a constant, which we called here d. We can use the rest of our given information, that at t equals 1, our position equals 3, to solve for d. By substituting 1 for t and setting the equation equal to 3, we'll find that d equals 6. So we end up with a good looking function, but now what? The ask was to find our position at t equals 3 seconds. And now we can actually do that. We have the position function in terms of t, so all we need to do is sub 3 for t. And we find that the particle is at 39 meters at 3 seconds, or option C.
This is the last part of the series for now, but make sure you check out parts 1 and 2. Remember to be kind to yourself when you're studying and learning anything new. It takes time. Good luck studying, stay curious, be sure to subscribe, and I'll see you next time. Ugh, my baby hairs.